Welcome back to Learning Solidity. Now in this tutorial I'm going to cover data types. I know what you're probably thinking, this is quite late on into the tutorials to really be covering data types, but as I've previously highlighted on certain data types before, what I plan to do now is focus primarily on arrays, mappings and structs, and then just give a very generic overview of all the other data types. Now on the Solidity documentation there is a page dedicated to data types, which I will leave in the description box down below. And what I'm going to do now is just jump straight into Remix. I've already created a data types contract. I'm just going to knock through the very basic data types first. So the very first one that I'm going to cover, obviously starting from primitives and working my way up, is a boolean. And simply defined by bool, I'm going to call this one my bool, and can either have a value of true or simply false. And that's it in a nutshell. So I'm not going to go any more detail than that because there really isn't any. Now the next thing I'm going to cover is integers. Now once again I've covered this loosely before in the past. Now there is two types of integers as previously mentioned with Solidity, but again similarly to all programming languages, you have signed and unsigned. A signed value simply means it can be positive or negative, and unsigned simply means it is only positive. Now with Solidity, similar again to quite a few programming languages, you can also define the length in bits of the integer. So for instance, I can say I want to create an integer of length 8 and call it my int. Now the only constraint you actually have there is the actual length you have in bits has to be divisible by 8, and that can only be a range of 8 to 256. So for instance 256 is fine, as well as 248 because again divisible by 8, but 245 is not. Now again you can have something very similar with the unsigned integer. Well, I say very similar, it's actually identical. So unsigned integer 8. Now obviously, because obviously that's a length in bytes, my int can be anything, if I'm correct with this, between 127 to minus 128, whereas an unsigned integer of length 8 bits, and I'm just going to call it my uint, can be a value between 0 and 255. So I'm simply going to define those by 128. What is it saying? I've got this as a goal. So moving on from that, we then have strings. Now once again we have covered strings, but I'm just going to highlight an issue that I've noticed when developing certain things with strings, and this is focused around arrays. Because of the way Solidity stores a string, again similarly to most programming languages, it stores it in an array of integers. Now traditionally most programming languages are referred to as a char, but in Solidity, if I'm correct, it stores it as essentially a, well, I'll first define a string and just call it my string, and in Solidity it's essentially going to be a struct, and within that struct what there's going to be is in essence an array of, I think it's either bytes, or in this case, well, I'm just trying to keep it simple, I'm just going to say it's an array of uint 8s. So that's essentially my string. Right, so when you actually create a string, what you're actually creating is an array of values. So for instance, when I pass into a function a string, I'm just going to call it my func, what I'm actually passing in is an array of values. I'll just call it my string again, or my string x, and I'm just going to call it s to make things simple. Okay, so we've got a function of passing in string. Now what we're actually passing in, like I previously mentioned, is an array. So for instance, if I were to pass in uint8 array, that's absolutely fine, you can pass that in. But because of the Solidity's current implementation, I believe this probably will be fixed in a later implementation, I pass in a string of arrays. Again, I now get an error saying unimplemented feature error, nested arrays not yet implemented. So that is just something to bear in mind when passing parameters to functions. You cannot pass an array of strings because an array of strings contains a nested array. Now that's all I want to touch on in regards to string because, like I said, we've previously covered it. The next thing I am going to just very loosely address, and I want to actually do a bit more expansion on this in a later tutorial, is bytes. So similarly to string, we can have, it's in essence an array of bits, essentially, or well, in bytes it's just always going to be an array of bytes, sorry, should I say. So even if you define byte, I can even type it, what we're going to do is see the actual true value of byte is actually bytes 1, because byte is actually simply just an alias to bytes 1. Now, with bytes, you can specify a range similarly to integer, so that can be a value between 1 and 32. It doesn't have to be divisible by 8. So, like I said, you can simply state that I want an array size of either 1 to 32, and that is applicable. I think it's 32. Yeah, it's definitely 32. So, like I said, because I'm covering this in a later tutorial, I'm going to just kind of skip on that for now. The next thing I'm going to cover is something that's kind of a little bit of future-proofing for Solidity. It's an unimplemented feature, but I feel like I should highlight it nevertheless. Now, this is essentially a fixed point number. So it's kind of, it's not in essence a floating point number, it's a fixed point. I'm not really going to go into the details of the two, but the easiest way to describe it is a fixed point number is something you should use in a financial system, whereas a floating point number is something you should use in geometry. You should never use a floating point number in a financial system because, if I'm correct, you can never guarantee the actual result, so therefore like either devising or adding two floating point numbers can result in an unpredicted value. So what the fixed point number essentially is in essence very similar to an integer, but an integer with decimal values. So you specify the keyword fixed, and I'm just going to call that my fixed. Now behind the scenes what that's doing is creating a fixed integer first of a value of 128 bits, and then assigning it the value, then basically assigning it 19 decimal places as well. What you can do is specify this yourself. So similarly to integer, we can specify the length in bits available to us. So 8, and then we specify the length of decimal places available. I'm just going to simply say 1, and that is our fixed point number. So that can obviously be like 255.0. Now, if you're actually trying to sign this, because it's not yet implemented, it will give you the following error. Is that really convertible? Actually, we want to just fix this by 128. Oh wait, yeah. In type. Oh yeah, I'm trying to sign. Just fix that altogether. Int const 128 is not explicitly convertible to the expected type fixed 8 by 1. Let's just say 1.1. Because let's try 8 by 8. We'll use explicit conversion. 256. There we go. So, sorry about that, I've not really done much with fixed point numbers. It looks like the actual length of the fixed point number in bits does actually incorporate the decimal placing of it as well. So that is just something to be mindful of. Now this also goes into unsigned integers as well, so you do the same for a u-fixed, and I'm going to simply state that's a u-fixed. So once again it's 128 by 19, so my fixed, and again you're going to get the same issue with this one of if you're trying to assign anything, it's once again an not implemented error. So let's just comment those out and move swiftly on. Because they're not fully implemented yet, I've not really had much chance to actually play with them, so I'm not too savvy with that as of yet. So again, that may be subject to change, but that is something that you want to be mindful of if you're ever sort of defining fixed point numbers or want something with a decimal place. Now the next thing I'm going to have a look at is a enum. So similarly to most programming languages, again you have an enum, which is defined as lowercase, and then you specify your name. In this case I'm going to call it action, and then we can simply define a list of actions with something like add, remove and update. What is wrong with that enum action? Oh, left bracket sign. We do not need an assign operator. So with our action, we can simply define it by saying my action equals action dot add, and that is a very simple way of using an enum. If I remember rightly, it does throw an error if you try and define it as an integer value. So for instance, if I just try and reference it like you would an array in very common programming languages, the int const 0 is not explicitly convertible to the expected type enum. So again, kind of similar to the error I was having with my fixed, but that's neither here nor there. So then jumping straight into addresses now. Now we have covered addresses before, but I want to cover just a little bit more functionality of what the address can actually offer as well. So I'm just going to call this my address. And to actually assign my address, what we do need to do is create a method that is payable. So actually, no we don't. We only need to actually create a payable if we want to access the value of my address. So we can create a function called assign address, and then that can simply be my address is equal to the message being sent, which is obviously the transaction interacting with this function, and then sender. So as previously mentioned in a tutorial, sender is the address of the person interacting with the contract. If you wanted to do it at the creation point, you would set this in the constructor. So that is basically how you assign your address. Now address actually has a couple of functions. What you can do with the address is call the balance. So my address.balance is a way of finding out the balance of the address, and you can also do my address.transfer. So you can actually transfer an amount of Ethereum to that specific address. And that is pretty much what functionality is enabled within the address scope. The next thing we're going to look at is arrays now. Now we're going to get a bit deep and dirty into arrays. As we've previously touched on it, well obviously when we were looking at strings. Now arrays can be defined in kind of one of two ways, and I'm going to just use an integer for this because obviously I've already highlighted the issues with strings. You can define an integer by simply stating, let's just go with a basic uint of no fixed length, and then just call it my int array. Now you can actually predefine your integer array as well by simply stating in square braces 2, 3. And that's a way of defining an integer like that. Now because obviously we've not defined a fixed length, we can actually append to this. So if I simply state function array func, what we can do is they take my int array.push and then add another value to it. And that should then simply have a length of 4. We can continuously do this because it's a non-definitive length. Now if you want to create an integer with a definitive length, we can simply state uint 10 my fixed array. Now obviously if we try and keep pushing that beyond 10, you should get an out of bounds exception, if I'm correct with that one. And that is basically the two ways to create an array. Now there's one function and one member attribute that you can use to access this array, and that is simply by my int array.length. Learn to spell. So you've obviously got the push, and the only other member attribute you can actually get from an integer is length. Obviously you can specify or reference a value, my int array as in 0, to actually access a direct value. And that in a nutshell is arrays. Now the next thing I am going to look at is actually I'm not going to cover structs because should I make structs first or mapping? I'm actually going to cover structs first. And the reason I'm going to cover structs first is because I'm going to make it part of my example of mapping. So with our struct, what we're simply going to define, or I should probably go into a bit more detail what struct is. Now if you're a JavaScript programmer, you probably this concept might be a little bit foreign to you. If you're a C programmer, you really should actually know what a struct is. It's, in essence, it's an object with no functionality. Now I know in C there was a way to actually do this with various pointers, but let's just keep it on its very primitive sort of terms for now. So inside our, let's create a struct. And within our struct, we're just going to have some basic things. So I'm just going to say it's an account. Now within our account, we're going to have a uint, which is going to be our balance, and we're going to say let's have another uint and let's call that daily limit. So what we actually have there is an account with a daily with a balance and a daily limit. Now to create an instance of our account, we can simply just state account and then call it my account. And now we have an instance of an account. And to access the sort of member attributes of a struct, we can simply say function struct func. Now within that we can then state my account and then reference balance, and you can do the same for daily limit as well. So you can also do assignments here as well. But obviously you do need an instance of the actual struct to be able to sort of manipulate values. Now the reason I did that first is because I'm now going to use my account in the example for mapping. Now a mapping in essence is either a hash map or a dictionary. It depends how you refer to sort of like I think generally in C, and definitely Objective-C, you refer to it as a dictionary, but Java programs and so forth will refer to this as a map or a hash map. So to create a map, you simply need to state mapping, and what we're going to say is we're going to map address, or the object of address, to our new account, and we're going to call this underscore accounts. Now what that essentially is a non-limited sort of an associative array essentially. What we can do with that, if we create a function for it and simply call that mapping func, is we can use, for instance, the sender, the message sender, to map an address to an account. So in this case we've got something called sort of accounts, and let's reference the message.sender, and we're simply going to say the balance is, actually let's define this as a starting point of 0, and we're simply going to say the balance is going to be plus and equal to the message.value. Now this is going to throw an error because we've not stated this as payable. Oh, you can't define a 0, but actually, to be honest, when you actually create a uint as 0, when you create a uint instance anyway, it's going to define it as 0. So what I'll do is every time that you pass a value to, or make a payable function call to mapping func, you will pass any value into your balance. So you can basically use this as a wallet. Now I wouldn't use this as a wallet. I'd go into a lot more detail because I've seen a lot of problems with these sort of wallets, especially the parity wallet. If you've saw the bug that went on with that one, just always make sure that if you are going to do something like that, ensure that you're actually securely programming it. Now that in a nutshell is pretty much everything in regards to the simple data types. Now we'll just create this as an actual actual contract and show you this using. I've changed that to the fallback function, and I'm also going to add get balance. And what I'm going to do with get balance is returns unit, and then that's simply going to return accounts message sender dot balance. Okay, so when I create this contract now, because I have a fallback function, if I send 10 Ethereum to the fallback function, and now if I get the balance of that, it should now be 10. If I then add another 5, call the fallback function, and then call the balance once again, it's then going to be 15. So this, like I say, is a way that you could actually do a sort of a wallet if you wanted to. But once again, I do want to highlight the importance of ensuring you get the correct security. So just be mindful of that when developing anything to do with a place you're going to be storing Ethereum, because the last thing you want to do is have it exploited. That in a nutshell is all the data types of Ethereum. There is a few other bits and pieces, but because of the general levels of complexity around them, as well as their current level of implementation, I'm not going to cover them now. like I said, I will cover bytes, but in a later tutorial. I'm also going to expand on the use of strings and string functionality again in a later tutorial, but for now I'm going to call it there. I hope you found this useful. If you did, give it a thumbs up. If you have any comments, leave them in the comment box below, and if you subscribe, that would be much appreciated. But for now, I will see you next time.